So let's start with today's session with the performance of an aircraft engines. Okay. So before proceeding with the performance, we will see the ramjet engine, and then we will move further what are the criteria that helps to increase the performance of the aircraft and decrease the performance of the aircraft. Okay. Aircraft engine. Okay. Here we are talking about aircraft engine. So all those things we have covered, the applications of uh, different kind of aircraft engines we have covered. We have covered the turbojet cycle. Okay, so what is actual behavior and ideal behaviors, also we have covered this part. Okay, and this is the one of the from the case study I got. Okay, how this engine performance varies in the adiabatic efficiencies. So sometimes the question can come in this way, that find out make an ascending orders of the efficiencies that we have studied: lot many efficiency, diffuser efficiency, compressor efficiency, combustion efficiency or burner efficiency, then turbine efficiency or the nozzle efficiency. So you have to align that how this combustion efficiency are interconnected with each other, right? Which one is a greater, which one is a higher, or they're equal with each other. So sometimes it might help you to answer that kind of particular questions. So you have to remember the some kind of ranges, right? So what is the range in between? Then next we have ramjet. Okay, so today we will see the ramjet, and we will see what are the performance criteria that it depends on, and we will solve lot many different kinds of problems so that you can get used to with this turbojet problem. Every year, almost every year, they are asking a problem from this particular topic, that is thermodynamic cycle of a gas turbine. Okay, so they will ask in a twisted form, but you have to understand and figure out, and you have to solve that thing. Okay, so we will move to the ramjet part. Okay, now ramjet, if I say, we know that unlike turbojet what we have seen, we have the intake, we have the moving parts. Okay, what are the moving parts? The compressor and the turbine are the moving parts. Then we have the combustion chamber. Then we have the nozzle. These are the five important parts we have. But in ramjet we do not have any moving part. That means it does not have any kind of compressor nor the turbine. It doesn't have neither the compressor nor the turbine. Okay. Then how it getting compressed? How the propulsion is taking place? Okay, let's look into it. But instead they have a different kind of supersonic diffuser. Let's look into this figure. So to simplify the ramjet air breathing engine, the first they have, that is 1 to 2. What you can see, this section is called as an, or you can see, okay, here it is mentioned that supersonic diffuser. First we have the supersonic diffuser, then this part is called as a subsonic diffuser. So here we have two kind of diffusers. One is when it is the supersonic, and next we have the subsonic, followed with, we have some space over here. Okay, then we have the combustor, then followed with a nozzle. So you know what happens in the diffuser, right? So why we have the supersonic diffuser, because you know the ramjet we use when the flight speed which ranges from 2 to 5, okay, 2 to 5 Mach number. So yesterday we have seen in aerodynamics, when the flight is moving more than Mach 1 or 2, we use a sharp leading edge. We use a sharp leading edge in case of wing, we have discussed. Now same as in case of the ramjet also, we can see over here is we have the sharp edge. Now what this does is, now you see the cross section. Now this is the air is coming. Now air is coming. When it is coming at this particular point, right, what will happen? It will create an shock wave. Will it create a shock wave, right? Now there are two, basically to understand that, okay, so remember there are mainly of two kinds. One is an oblique shock wave, another one is the expansion shock wave, okay, oblique shock wave and expansion shock wave. Now when this oblique shock wave occurs, suppose consider now I am having some plate, okay, plain plate, flat plate, A point, B point, C point. All the A to B and B to C are 0 degree. Okay, A to B plate and B to C are 0 degree. Now, and what I am doing, A to B is 0 degree. With respect to that, I am changing or inclining the plate at some angle 10 degree. At an angle 10 degree. Okay, that means this is a B point, A point, this is a C point. I am inclining upward. So what I am doing is I am inclining upward. So what will happen when the flow comes over here, right, the free stream. So from this point what will happen, it will cause an oblique shock wave. It will cause an oblique shock wave denoted by beta, okay, denoted by beta of oblique shock wave. And when the flow comes and hit over this flow, again when it leaves from the across the shock wave, the flow will be parallel to this surface called BC. When the flow leaves, it will be parallel to the BC. Now what is the change in the property? Because there is a formation of oblique shock wave, let's consider this is a region 1 ahead of the shock wave and behind the shock wave, right, there are two kind of regions are separated. Now if the Mach number is greater than 1, let's consider M1 is Mach number greater than 1 if the pressure is P1, okay, we are considering the pressure, static pressure alone. Now what will happen with the behind the shock wave? The Mach number decreases, that is M2 in the region 2 get us M1. The Mach number decreases. Mach number means what? I can say the velocity decreases, but the static pressure, the P2, increases. P2 becomes greater than P1. Okay, P2 becomes greater than P1. That means when the air is coming and hitting over the surface of this supersonic diffuser, what is happening over here? That means there is a built-in pressure. So you don't need a separate kind of compressor. Now what is the act of compressor? To increase the pressure. The fundamental reason of the compressor is to build up the pressure in case of turbojet engine. But here in the ramjet, using this supersonic diffuser, what is happening? It is building the pressure. Okay, and this compressed pressure is flowing over the combustion chamber, where the fuel and this compressed air get mixed, okay, get combust and expel out from the nozzle. Okay. Now talking about this oblique, let me just give a brief intro about the expansion wave also. Now when we have the expansion wave we have that, as I said, the plate A, B and C. Okay, let me erase this part. So alright. Now we have the plate. Okay. This is the A point, B point and C point. Okay. Now when this BC is deflected downwards, so what will happen here? When the free stream comes along the AB, right, it reaches in the point B, it will cause an expansion fan or expansion wave. Okay, expansion wave, and when it comes over here, right, and the downstream flow is always going to be parallel with the surface. So what is the surface? BC is the surface, and the free stream flow across the wave, or the expansion shock wave, will going to flow parallel. Now what are the property changes over here? As you know, again we are concerned with the Mach number. The shock wave means the Mach number has to be greater than 1. So this is the two regions are forming here also, 1 and 2 region. So if Mach number is 1, greater than 1, let's consider the P1 at the, that is some kind of static pressure. Here we are talking about static pressure. Okay, static pressure at the region 1, right? So across the expansion wave, what happens here? The Mach number increases. The Mach number, the M2, increases as compared with M1. Suppose you have the Mach number 2. So if it is undergoing under some kind of expansion, so the Mach number has to be at least more than Mach 2. That is, it has to be at least 2.1 or 2.2 or 2.4 and so on. But what happens if the velocity increases? What will happen with the pressure? That is P2. If the velocity increases, the pressure will be acting in the opposite way. Then pressure will be less than P2. Sorry, P1. P1. Okay. Alright. So here the pressure will be decreases. But in the oblique shock wave, what happens? Across the oblique shock wave, the Mach number decreases and the pressure increases. Okay. That's why based on the same principle, if you see in the rocket engine, right, they have in the rocket nozzle, if you see after the throat, okay, when the air comes over here, so each and every angle it is decreasing, okay, the wall angle has kept in such a way that it always cause an expansion fan. So due to the formation of this expansion fan, what happens, the Mach number accelerate from the nozzle is always increased. If the nozzle exit or the jet velocity is increased, then obviously the thrust will be improved. Okay, and that is the main reason that we give before we have the conical nozzle and now we have the bale nozzle, and because of formation of the bale nozzle, it creates an expansion fan or the expansion wave. So now coming back to the ramjet, so again I'm telling you, you have to be get ready with any sort of question or interconnectivity they can ask you from any kind of topic. Okay, now here if you see the topic, here it is again the mixed domain of the aerodynamics and the propulsion, right? So they can ask you the combined effect of that. They can give you the engine and they will ask you where will be the pressure difference of each and every domain. So yes, so once it gets compressed, now what happens, this compressed air enters in the combustion chamber. Okay, now here the compression ratio is near about, when the this compression ratio is taking, it is up to 8 to 10 compression ratio. It is near about, takes place 8 to 10. Okay, very high ram pressure is taken place. But what happens when the flow comes over here, right? As we have seen the oblique shock wave property, what is the oblique shock wave property? The pressure increases but the Mach number decreases. So since here the Mach number, suppose it's greater than 2, okay, so what will happen when it is coming in the combustion chamber, the velocity get decelerated, okay, or the velocity decreases. So when it is coming to the combustion chamber, the Mach number is almost near about 0.3, okay, near about 0.3 when it is mixing with that. Okay, then what happens, it gets combusted and again it expels out from the nozzle. Now here you see in the nozzle we have the divergence section. Now here we have the divergence section. Now what is the property of the divergence section? We have seen what will happen if the Mach number, what is intakes over here is, let's consider intake is M1 and expelling out is M2, right? If the area increases, area gradually increases, right? Here we have the divergence section. If the Mach number is greater than 1, if the area gradually increases, the M2 will be increases, M2 will be greater than M1, M2 will be greater than M1, right? So this is the again another concept, because this is flying at Mach number more than 1 or 2, right? So since it is flying at more than Mach 1 or 2, that is supersonic speed, right? So we have to use a divergent nozzle. Okay, but unlike if you see in the turbojet or some other turbofan or something which is ranging within the 0.9 of Mach number, where we have the convergence section, Not only that, if you see the diffuser section. The shaft, it is a kind of blunt shape, but if you see in the ramjet, it is a sharp leading edge. Okay, sharp leading edge. Okay, all right. Okay, and one more important fact is the temperature, which ranges in that combustion chamber near about 15,000 to 2000 Kelvin. Okay, 15,000 to 2000 Kelvin. Now coming to the sum of the thermodynamical cycle. Okay, so to find out the efficiency and the other parameters, this is an ideal cycle. So ideally we consider mi equals to mg. Mi is the when it is entering, okay, that is a flight speed, and mj is an exit Mach number. So ideally we consider this, ideally we can write that inlet, or I can say the flight velocity, is equal to the jet velocity of the ramjet. Now we know what is Mach number. Mach number is V by A, where A can be also written as in terms of gamma R T. Now we can rewrite this equation as Vi by root over gamma R T I, or T1 you can consider. Then similarly in E we can write VE by root over gamma R T E. So either you can write Ti equals to T1 and Te equals to T4. Right? Either of the convention you can use. So based on the fact, whatever the parameters will be given to you, you can find out the value. Right? So V equals to, you can write Vi root over T4 by T1. This is only for an ramjet engine. Now, okay, there is one more formula to find out. Yes.
And this is for ideal case, no?
This is an ideal case, absolutely. This is only for the ideal case. Okay. And one more formula is there for ramjet. Okay. Note down the formula. This is for ideal efficiency of the ramjet. This is 1 by 1 plus 2 by gamma minus 1 by 1 by m square. This is another formula to find out the efficiency of the ramjet. This is an ideal condition. This is in ideal condition. Please note down the values, because we will solve some of the problem based on this. Okay. So can I say from this equation, which we have seen in Brayton cycle, right? Brayton cycle. If we have the pressure issue, can we use this formula? This is an ideal Brayton cycle. Can I use this formula? Similar way, right? So what is RC? Is a pressure ratio, right? Pressure ratio. So right? That is RC. So either of the way they can give you. Okay. Now what this expression says, that when possibly my efficiency will improve. What are the ways that my efficiency can be improved? How this efficiency are dependent in terms of pressure ratio and in terms of Mach number. How I can say that? Can I say same as that what we have seen in Brayton cycle? If the pressure ratio increases, my efficiency will also improve. That means if the pressure ratio is improved, means my Mach number will also increase. My Mach number will enhance to increase my Mach number, right? So if the Mach number increases, then indirectly my efficiency will also increase. Okay. All right. Now here is that profile, that how the pressure and the velocity is increasing. So you can understand in the diffuser what is happening. Initially the velocity is decreasing, right? After the fuel injection, then gradually it starts to expel, and kinetic, it just got its kinetic energy, right? And if you draw a line, you can almost find that almost the intake velocity is almost equal to the exit velocity or the jet velocity. Okay. But what happens with the pressure? In the diffuser, the pressure gradually increases, right? And as in the range of combustion zone, the pressure gradually fall, and in the nozzle it just fall in a steep way, in a steep pattern. And finally again you can see the whatever the pressure when it enters and the exit pressure is also same. The intake pressure and the exit pressure, the finally it's also same. This is in case of ideal ramjet, okay, from the ideal ramjet. So they can also, you can also expect some kind of questions like that. Even one of the year they have asked such kind of question. They have given you the ramjet, okay, ramjet engine, or it can be of the turbojet engine also, and they will give you various kind of this here Mach number or the pressure, okay, Mach number and the pressure they will give you. In a similar way, you have to find out that where the pressure will be high and the temperature will be high, and so on. Okay, so accordingly you have to put up the choose the values. Okay, so there are certain advantages and disadvantages that you study, because sometimes they can give you like kind of statements, and from the statement they will ask you find the best or suitable one for the particular engine. So the advantages and disadvantages I am not going in depth, so you just study by yourself. Okay, so I will give that in the notes, the advantages and disadvantages. Okay. All right, so let's see a bit detailed performance of the ramjet, because again there are lot many questions they are asking based on the performance of the engine. Okay, performance of the engine. So let's see what this says. So at low flight speed, the thrust fuel consumption is quite high, while at the high speed it reduces. So ramjet is more efficient. That means, what is mean by fuel consumption? We are talking about that how much fuel is going to be used, right? So we know if we are talking about SHC, okay, so if it is having the low efficiency, low TSFC, means it will increase the efficiency of the engine. If we have high TSFC, it will decrease the efficiency, right? So we need to improve always we have the motto to improve the efficiency. So to improve the efficiency, we need to decrease the TSFC. Okay. Now how we can then, only for the ramjet it will be more efficient if it flies at a high Mach number. It is possible when it flies at high Mach number, then only it is possible. And why it is low? Because at low speed the compression ratio is not proper, because in the ramjet we don't have any compressor nor the turbine, right? No rotating components we have. So only way you can compress by increasing the Mach number, right? If you decrease the Mach number, the compression ratio will be ineffective. Okay, so that's the reason. Okay, that's the reason we have to achieve the low TSFC to improve the efficiency. And when we can do, when we have the highest Mach number. Next one, this is the thrust is maximum at the sea level and decreases as the altitude increases. So that means the thrust is only maximum when at the sea level. Okay, so you can see in this graph that this is a Mach number with an net thrust. Okay, so when we can produce a high, this is the points. Okay, these are the points. So as we increase in altitude, this is an increasing order of altitude, increasing order of altitude. So what we can see, gradually the thrust is falling. Okay, why? Because of density. Because as we increase in altitude, what happens with the density? Density also decreases, right? Density means we can say again in terms of mass flow rate, right? So if the mass flow rate is more, the thrust will be more. If the mass flow rate is less, then thrust will be gradually fall. Next, so the thrust at a given altitude, the rises rapidly with increase in the flight speed due to the increases in pressure ratio. So this is another point, the thrust can be improved. Okay, how? If we are increasing the pressure ratio. This is another point, the thrust will be increased, okay, if we are increasing the pressure ratio, because increase in pressure ratio increases the flight speed, increases the flight speed. See, these are the very key points. Okay, these are the very key points. You can never expect how they will frame out the question. Okay, so the performance of engine, whatever the engine it might be, the connectivity is very much important. And sometimes this topic, sometimes in this performance of this engine can also be connected with the flight dynamics. So again, when you are going to study the flight dynamics, again you will have a brief recap about this topic also. Okay, because another important factor will be seen, the thrust loading, or I can say thrust to weight ratio. Now thrust to weight ratio also one of the important factor to understand how we can important factor to improve the engine performance, important factor to improve the engine performance. Okay, this is another important parameter we will see, and we will see how these factors are also help to choose the right engine. Okay, this is also will be connected with L by D ratio. The thrust to weight ratio will also connect with L by D ratio. L by D ratio will be connected with the range, and based on the range we can select the appropriate engine. The appropriate engine choosing will help to decrease the SFC. The choosing of appropriate engine will help us to reduce the SFC, because we need to decrease the SFC. If decrease the SFC, we will improve the efficiency. Okay, so in the performance, when you are studying, always try to connect the things, how the parameters are interconnected with each other. Okay, all right. Then yes, throughout the ramjet it can operate in subsonic velocity also, but it will be more efficient if it is flying at high altitude and the velocity within this particular parameter. Okay, please remember the numbers. Now here they have given in kilometer per hour. Now either you can convert that in terms of Mach number. Okay, either you convert that in terms of Mach number or in terms of meter per second. Okay, so you have the values both in terms of kilometer per hour, Mach number, or in terms of meter per second. Right. Now how to convert kilometer per hour to meter per second? Suppose you have 6000 kilometer per hour, right? So 6000 into 1000 we get in meter, then hour we have. Okay, so when you solve this, okay, you get 5 by 18. So whatever the value, you just multiply 5 by 18, you will get the value in terms of meter per second. Alright, so now we have one problem. So let's read the problem first. A ramjet engine operates at a Mach number 1.5 at an altitude of 6500 meter. The diameter of the inlet diffuser at the entry is 50 centimeter, and the stagnation temperature at the nozzle entry is 1600 Kelvin. The calorific value of the fuel used is 40 megajoule per kg. The property of the combustion gases are same as those of air. The velocity of the air at the diffuser exit is negligible. Calculate the cycle efficiency of the ideal cycle and the flight speed. Okay. Now how you can find? You know the efficiency. What is the efficiency formula? Ideal efficiency plus 2 minus 1. This is the formula. Operates, M1 is given, right? M1 is given. Substitute the value over here. Gamma value is given, and tell me the answer. Substitute and tell me the answer. Substitute and tell me the answer.
Zero 0.08, ma'am.
0.08. Sorry. Sorry. There is an error in the formula.
I'm getting 0.08 only.
See, I have just written the formula wrongly here. It is this one. Okay, this is the formula. 1 plus of 2 by gamma minus 1, 1 by m1 square or mi square. This is the formula.
0.310, ma'am.
Yes, 0.310. If in percentage, 31 percentage, right? Now they have asked, this is done, they have asked the flight speed. Okay, they have asked the flight speed. How can you find the flight speed? Now one data,
Mach number equals to
yes,
Mach number equal to
v by a,
A.
right? Now they have given at altitude 6500 meter. Okay, in the given data one more thing is given, that at this particular altitude, okay, the temperature is 2491.90 Kelvin. Okay, T is given as 249.90 Kelvin. Now how we are going to find out? You need is to find this, then gamma r T value, right? So T value you are going to use 249.90. So using that,
475 meter per second, ma'am.
okay, that means you are getting V equals to 1.5 into root over gamma r T. You are getting around 475.31
0.31
meter per second, right? Okay, you are getting this value, right? All right. Now,
Yes, ma'am.
all right. Now from this question, okay, though there are lot many possible ways they can ask based on the given data. Okay, they can also ask you find out the mass flow rate of air. Since they have given the mass flow rate of the gas and the air are same, so the mass flow rate enters in that uh, the ramjet and expels out will be same. From the continuity equation they can ask you find out the mass flow rate of air. Now if they ask to find out the mass flow rate of air, how you are going to find? What is the formula? Rho a v. Okay, so what will be the rho? If they have given the property of the rho, you will get the rho value, right? A, they have given the diameter, so you can find pi by, okay, just give me a second, it is creating some error. Pi by 4, okay, d square, change the unit over here, okay, into velocity. Just now you found out the velocity 475.31. okay, so using that you can find out the mass flow rate. Now always the mass flow rate unit is kg per second. Okay, all right, so this is how you are going to find out. Then similar way the other parameters or interconnected parameters they can ask you. All right, then next.
When they will give the temperature or just altitude, and
They
we
have-
have to find the temperature.
No, if here they have not given, right? So the given, it will be in the given data, okay, because here actually they have given, I forgot to keep it over here. Okay, the temperature has been given based on this particular altitude. The temperature has been given, it has to give. Okay, otherwise what they do in the gate, in the first page they will have some particular standard given data. Okay, so you can use that also. Okay, all right. Okay, now coming to a very important part is a thrust equation. Okay, so we are going to see how this thrust equation, what is the significance, and so on other parameters. Okay, so again we are not going much into derivation part, but yes, what are the factors, significant parts, we will definitely look into that. Okay, so what is thrust equation formed. There is a jet engine, right? Again we are coming back to jet engine. So the intake pressure considered as PA, the expelled one dot the exit pressure is considered as PJ. You can either take PJ or PE. Okay. Then intake pressure, intake velocity is CA has been represented, or you can consider VA or VI, any one of the convention. Okay. And expelling out you are considering as VE or CJ or VJ, or the jet velocity. Okay, any one of the convention is okay. But the thing is, you have to understand what is CA, CJ, VA, VI, VE, VJ. Okay, do not get confused with that. So here, though the equation are giving in CJ and CA, but I will use this particular convention. Okay, VE and VA. Okay, so do not get confused with these parameters. Okay, now what is the thrust equation? It is a sum of the moment thrust plus the pressure thrust. So when the summation of the thrust can be produced by means of the moment thrust and the pressure thrust. Now what is a moment thrust? Moment thrust is when this is the moment thrust. Okay, so if I have to write the moment thrust like this, it is thrust, or I can write T equals to m dot of E, that is a mass flow rate expelling out and mass flow rate intake. Okay, intake I will take as A, exit I will take as E. So mass flow rate in expelled into exit velocity minus mass flow rate of intake into the velocity, plus when we simplify that equation we get exit area, we do not consider the one, AE by PE minus PA. So this one will be the pressure thrust, and this one will be the momentum thrust. Okay. Now what is ME? What is m dot E? M dot E is a combination of mass flow rate of air plus mass flow rate of fuel, right? So can I write that dividing both in terms of mass flow rate? Okay, so we get the mass flow rate of intake by mass flow rate of air, we will get 1 plus F. And what is F? F is the mass flow rate of fuel by mass flow rate of air, right? Now using that relation we can use this particular relation, what you can see in the thrust, that is m dot I is what? Is the intake into 1 plus of F of VE minus VA plus PE minus PA into AE minus PI and PA will be 0. Okay, PI, because intake and the ambient are going to be same. Okay, here we are considering the ambient and the intake pressure is same, so this value will turn to be 0, and finally we get this equation. So it can also get like that, 1 plus of F VE minus VA plus AE PE minus PA. Okay. Now in that case again, if PA is equal to PE, if I consider the ambient or the intake pressure is same as the exit pressure, so what we'll get, then our pressure thrust will tends to 0. Then what will happen, the pressure thrust will be 0. Now you can get this kind of question that in a thrust equation, if in a thrust equation in a ramjet in a gas in any gas turbine engine, if the ambient pressure is equals to the exit pressure, then what will be the impact in the thrust or the moment thrust or the pressure thrust. So you can expect such kind of twisted question. So if you know the ambient pressure, you have to remember the thrust equation. So you know the thrust equation is this one. So if PA equals to PE, then pressure thrust will be 0. Then you will have only the existence of movement thrust. Only the existence of movement thrust. And what will be the equation? Only you will have this particular equation. That is m dot A 1 plus of F VE minus VA. Now in this further thing, if they say the fuel consumption is much negligible, okay, the fuel fraction, the reactive fuel fraction is much negotiable, okay. So again we can further reduce this expression in thrust equals to mass flow rate of air, that is VE minus VA. Then we don't need to write down the air even, we can simply write m dot. In fact, m dot equals to VE minus VA. When we can write, when F is very less than 1, almost negotiable. So that time we can write in terms of VE minus VA. Okay. Now one more important fact. Shall I erase this part? Let me know.
Yes, ma'am, you can erase it.
Alright. Now one more important, in case of sometimes some kind of question they ask, in case of propeller engine, okay, propeller engine. Now consider this is your propeller, right? Now when the airstream comes, okay, comes and hit the blade, right? So let's consider when it is coming, that is V1, when it is hitting the blade, that particular, the propeller blade velocity is V, and what is expels out is V2. What is expels out is V2. Okay. Now in that case, what happens? The flow pattern is somewhat like that. Okay. That means when the V1, that is the upstream flow, comes and hits the propeller blade and it lifts back in the downstream pattern, some amount of, so I can say the V2 is less than V1, because some amount of kinetic energy, there will be losses in some kind of kinetic energy, okay, some kind of losses in kinetic energy, that means velocity decreases. Now if the velocity decreases, then I can understand that if I look into some of the control volume of this upstream pattern, that is, let me consider A1, and at this point A, okay, the area or the swept area, and at the point 2 when the downstream A2, so I can say that A2 will be greater than A1. A2, that is the cross sectional area on the upstream of the propeller blade, will be less as compared with the downstream location. Okay, so they are having some kind of connectivity with, again with the Bernoulli's equation, and the same way with the continuity equation, and from that if you have to find out the some kind of relations with that, so to find out the propeller blade velocity or the disk velocity, that is V should be the average value of the upstream and the downstream value, the upstream and the downstream value. Okay, so this is for the propeller blade. Okay, the upstream, the average, the velocity of the propeller blade should be the average of the upstream and the downstream. Suppose in case they give such kind of statement. Okay, so please keep that in mind. So if they ask, they have given the upstream value and the downstream value, and they ask you to find out what will be the velocity in the propeller blade, then you have to use this value. Now similarly they might ask you that mass flow rate at entering into the disk, so that time you have to use this formula, mass flow rate equals to rho V A. So A will be the propeller swept, or I can say swept area, right? The rho is the density, right? And V should be this. They might give you, if it is mentioned, the upstream or any kind of downstream. Okay, all right. So this is also one of the key point. Okay, so yes, so this is we have done same. Now coming to that, this is a thrust. Now what is another important parameter is a thrust power. Okay, these are the possible kind of problems you can expect on the small minute expressions. Okay, so there is a difference between thrust and thrust power. Now what is thrust power? From the power itself we can understand it is a product of the thrust and the intake velocity. Okay, the thrust into, or in the flight mechanics we have done the power available and power requirement. What we do, the thrust is equals to the velocity. So what velocity we are taking? Thrust into the VA. So when we multiply that, we get that mass flow rate into VE minus VA into VA. Now in case the fuel value is given, then you have to use this formula. If the value of fuel has been given, the mass flow rate of air, then 1 plus of fuel, then VE minus VA, that is a thrust value, into VA value, will be giving you the thrust power. This will give you the thrust power. But once the fuel flow rate is neglected, so you will get this value for the thrust power. Now similarly we have the propulsive power. Similarly we have the propulsive power. Propulsive power. Propulsive power is a combination of the thrust power. Thrust power they denote as P suffix T. Okay, P suffix T, and propulsive power denoted by capital P suffix P. So propulsive power is a summation of the thrust power and absolute kinetic energy of the jet. So again you can get that what you understand by propulsive power. They can ask you that how it is combined. They can ask you separately that find out the propulsive power alone. Okay, to find out the propulsive power alone. Now you have to just remember this basic formula. Okay, m dot a VE square minus VA square. Now what is VE? I said exit, and VA is a intake. Okay, this is the formula. So if the given data, they have given you the mass flow rate, exit and the intake, then you can find out the propulsive power. Alright, now let's see what are the factors that thrust can possibly varies with a constant mass flow rate and with a next we will see with a variable mass flow rate, if the mass flow rate is varying, okay, and with a constant mass flow rate. So this graphical representation will give you the significance of how the thrust okay varies or connections with an mass flow rate at different factors. Okay, at different factors. What are the factors? With the variation of the pressure thrust, moment thrust, the ram drag and the gross thrust. Okay, so here we were considering the mass flow rate is constant, the constant mass flow rate. Okay. Now let's look in the first curve. Now what it explains, okay, the significance of this graph. So we can see as the flight speed increases, right, if we have the mass flow rate constant, okay, mass flow rate is constant, if the flight speed increases, right, the pressure thrust remain fixed. That is, if the pressure thrust is an 42.4 kilonewton, that means it will remain fixed. Okay, at constant mass flow rate the pressure thrust will remain fixed at increase in flight speed. Okay, that is a one significant point. Let's see the next significant point. What it happens with increase in flight speed, okay, with increase in flight speed, again if you see this curve, it shows that the moment thrust will also remain fixed. As we increase in flight speed, okay, the moment thrust will remain the same, Next, what happens with a ram drag? Okay, ram drag. So as we can see, as the flight speed increases drastically, the ram drag will also increase. When the ram drag will increase, that means at a constant mass flow rate. The mass flow rate, that is how much amount of air is intake, the combustion process goes on and it expels out. When that process is constant, with that constant process, if the speed is only increased, there will be a drastical increase in the ramjet. Okay, drastical increase in ram drag. Next shows considering the overall thrust, since what is overall thrust? The combination of the pressure thrust and the moment thrust. If the combination of that, if the mass flow rate remains same and with increase in flight speed, if the pressure thrust remain constant and the moment thrust, then definitely the gross thrust will also remain constant. The gross thrust will also remain constant. This is in condition with an constant mass flow rate. These are the very significant points. Okay. Next, let's see what happens the thrust variation with an variable mass flow rate. Okay, the mass flow rate will be vary. So let's see what happens if the mass flow rate changes at some point. Okay, now first curve you see, if increase in flight speed, that there is no change in pressure thrust, because if you look into the formula, there is no subject of the mass flow rate. Okay, there is no subject of the mass flow rate, so there won't be any, it won't be affecting on the pressure thrust. It will be same, either it is a constant mass flow rate or it is a variable mass flow rate. The pressure thrust will be same, because what is pressure thrust? It is a PE by PA into AE. So pressure thrust will only vary if there is changes within the exit area of the nozzle. Okay, exit area of the nozzle, then only that will affect the pressure thrust, or the change in exit pressure and the ambient pressure or the inlet pressure. If there is any change, then only it will affect on the pressure thrust. Now moving to the next is how it will affect the movement thrust. I request all of you to note down these key points. Okay, key points, whatever I am explaining, note down these key points, what it expresses. Now in case of mass flow rate variation, okay, now as we increase, what is the momentum thrust? We have some factor of mass flow rate into VE minus VA, right? This is the momentum thrust. That means if we have some variation in mass flow rate with increase in some flight speed, right, the moment thrust will also increase. It isn't that means at this point, if I am having 1000 km per hour, right, I will get my moment thrust to be 20. If I am going to 2000 km per hour, my momentum thrust will be 40. That means it is increasing the value, right? Okay, next let's look into this ram drag. Now ram drag will also gradually, this is a linear increasing, okay, linear pattern. This is the gradual increasing pattern. Okay, as we increase in flight speed, it was a linear increasing pattern. Now what happens in the constant mass flow rate? Here it is also linearly increasing, but here the curve shows it is not linear, there is some the gradual variations, okay, in case of variable mass flow rate. Then moving to the next is that what happens with the gross thrust. So again, the gross thrust is a combination of the pressure thrust and the moment thrust. Since it will only affect, the gross thrust is a combination of the moment thrust and the pressure thrust. So this is not going to affect, only going to affect with the moment thrust. So the gross thrust will also, can see it is in the increasing, linear increasing order. So as the flight speed increases, the gross thrust will also increase. Now till here, any questions, any doubt? Could you able to follow? Just let me know. Could you able to follow the significance? significant factors.
Ma'am,
Yes, Abhijit.
ma'am, VA means velocity at ambient, ma'am, ambient velocity, right? Velocity of air.
No,
VA.
this is a flight velocity we are considering. That is VA.
Ma'am, no. Ma'am, exit velocity will be varying, no, ma'am, at flight speed.
Yes, that will be varying.
Then that previous the slide, ma'am, in the case of momentum thrust versus flight speed, there should be an increasing curve, right?
Which one?
Second one, ma'am, flight speed versus momentum thrust.
Here?
Ma'am. Flight speed as varying, ma'am. Same exit velocity also varying. So means it should be an increasing, right?
See, here we are only considering the mass flow rate remain constant. Other factors will be
Yeah.
dependent, right? Other factor here we are not telling that other factors. See, uh, here thrust is equals to, let's consider the pressure thrust is 0. Okay, this is the formula, right? VE minus VA.
We-
Now we are only keeping this one as a constant. I am not telling that exit velocity is also 0. Sorry, exit velocity is also constant. If I say that, then if I say this, then I can relate with that what you are telling. But here we are only talking with the mass flow rate. Okay. Suppose for an example, our mass flow rate is 1. Okay, let's consider mass flow rate is 1. Our exit value is 500, and we are inlet is 100. So what will I get? I will get around 400 Newton, right? Next, I'm increasing. If I'm keeping it constant, now I'm keeping the constant 500. Now I'm increasing my speed 200. Okay, what I will get? That time my thrust will decrease. If I'm fixing my exit velocity, and I'm only increasing my flight speed, what I will get? My thrust value will decrease. But here we are not talking about the thrust value. Okay, here we are not talking about the thrust value. With respect to that, this value is also fluctuating, varying. We are just only comparing how in case of Mach number these factors are varying with each other. Okay, this is a variable. If I see that this is a variable here, accordingly this VE value is also fluctuating. Got it? But in case the
Yeah.
question you have pointed out, that's a good question. Okay, but in case if that value is fixed, then the thrust has to decrease. Then it has to be something like this. Okay, then the value will be something like that. You got the point? Now you can also expect such kind of question. Okay, you can also expect such kind of question. Okay, if the pressure thrust is 0, on that condition, if the mass flow rate is also remain constant, if increase in flight speed, okay, what will be the variation of the thrust? You can expect such kind of question also. Okay. Alright, so here also the same thing with whatever I have explained, how these things are important. So considering the fact, the pressure thrust, now what are the factors that pressure thrust depends on? It's an turbine inlet temperature, and also it's called as a TIT. Okay, TIT. Then flight altitude, that means I can talk about density. Nozzle outlet area, that is AE, and the pressure, either it is the exit pressure or the ambient pressure or the inlet pressure. Okay. Now moment thrust, it depends on the jet velocity. Okay, the VE value. So these are the lot many parameters that how this dependency factor depends on each other, what are the conditions, the possible conditions it can have. So this kind of factor is a little bit theoretical, so please go through them, that when and what conditions the factors will change. Okay, so moving to that important part. Yes, so this also yeah, just now we have discussed this point. What will happen if the exit gas velocity is constant and the air velocity is increased, then what will the difference of this both the velocities will be decreased, that will decrease in the thrust. Just now we have discussed this point. So the graphical representation should be something like that. See, two possible things, not two, three possible things. Okay. One, you have to understand the equation. Okay. One, you have to understand this basic thrust equation. Now from the equation, if one of the factor is constant, right, how the other component going to react? Okay, the significance. Now from the significance factor, you can either obtain a graphical representation. Now from the graphical representation, you can analyze that with the increase in flight speed, the thrust is gradually decreasing. Now at what condition, at what point of time? Okay, either they can ask in a form of statement, okay, that this is a statement, the thrust decreases, or they can give you a graphical representation, right? So either of the way you have to get ready. Okay, so based on the parameters, they can either give you in the graphical representation or by means of statement. Okay, the decreases means this is a negative curve, which is a negative curve means it is a decreasing order with an increase in airspeed. Okay, and if you have something graph like this, it is in positive order, that is an increase in this direction, here there will be increasing. So you have to understand the pattern of the graph, and based on that you have to understand the statement whether it is a decreasing order or the increasing order. So again it depends on the ambient temperature and the pressure. Again it comes with density and pressure. So you can understand from this graph, you can easily understand from this graph how these factors are increasing the pressure. As we increase the ambient pressure, the thrust is improving. From the graph I can directly say, right, as we increase the ambient pressure, my thrust is going to improve, but as I am increasing the ambient temperature, my thrust will decrease. Then yes, significant points, the specific thrust of the turbojet. Now these are the formulas that you have to remember. Okay, what is specific thrust? Is nothing but the it is also called as a thrust per unit airflow. Okay, that is thrust by mass flow rate of air. So what is thrust in general? If the fuel flow is considered to be negotiable, that is m dot a into VE minus VA. This is the thrust divided by the mass flow rate of air, that is m dot a. Now we can cancel off this term, so we get VE minus VA. Now if they are asking the question something like that, that what is a specific thrust, so you have to give. Now the specific thrust unit, if you see, the unit is something Newton per kg per second. or it is also can be say as Newton second per kg. But if you see the specific impulse, right, specific impulse, as they have said that it is also same as specific thrust or specific impulse. Now there is a slight change in specific impulse. The unit is in second per second, sorry, second. The specific impulse unit is second. Now how we get the thrust per weight flow rate? The change is a weight flow rate. That means we are just thrust per mass flow rate of air into gravity into g. So when we get that, we get in terms of second. The unit is in terms of second. Okay. So if the question they have asked the specific impulse and the specific thrust, this is a difference. Yeah, please.
Then what is the denotation difference, ma'am? How to denote specific thrust and then
Yes,
specific
yes,
impulse separately?
yeah, they denote as F suffix x.
A specific thrust.
Yeah, this is a specific thrust. Okay. See, these notations vary from textbook to textbook. Okay. Again, so because it is all the creations of like to simplify some factors. Okay. So these are the simplification factors. So in one of the textbook they have mentioned that F suffix s as a specific thrust and specific impulses I suffix sp. Okay. And right now one more factor we have is a speed ratio. Okay, we will see speed ratio. Speed ratio denoted by sigma. It's not necessary that it has to be sigma, but one of the author's convention has been considered as sigma. Okay. Now what is speed ratio? It is the ratio between the speed of the flight by the jet velocity, that is the intake by the exit, or I can say VA by VE. Okay. Now how I can relate this equation? Now can I say this equation like if I take VE outside, V1 minus VA by VE. Can I write like that? So VE by 1 minus sigma. Now here they have taken alpha. Now it again depends on author to author, right? You can either take alpha, you can take sigma. The main thing is it is a ratio between the intake air or the flight speed by the jet speed. Okay, flight speed by the jet speed. Now each and every expression gives the significant term. Okay, significant term. Now what it shows the significant term is to achieve the larger specific thrust. If you want to increase your specific thrust, what you have to do is you have to keep the speed ratio small. You have to keep the speed ratio smaller, right? You can understand from this expression, right? You have to maintain the speed ratio smaller. Okay. Now also you can also find out one of the statement from this equation. Just a minute. Okay. So another important thing what you can understand that if we are keeping this jet velocity constant, that is the exit, okay, this exit one is constant, okay, exit velocity is constant, it is not varying, then how it is going to affect the specific thrust? Now can it what will happen? Just take an example that specific thrust we have, like let's fix that 500 is a specific thrust, 500 is a flight velocity minus 100, right? What is the difference? We are getting around 400. Now let me keep it fixed. 500 minus, I am increasing the flight speed, So what I am saying, simultaneously as I am increasing, let me keep it 300, so I can getting this. That means if I am increasing the flight speed, I am decreasing my specific thrust. I am decreasing my specific thrust. Now I can say in other term also. Can I say the difference, or can I say the difference in the pressure, difference in the velocity? Can I say that this is VE minus VA, the difference in the velocity, right? If it is high, then definitely my specific thrust will also be high. Can I say if the difference is high, right? So what is the difference? The 500 minus 100 is 400. Now I am decreasing the differences. I am getting low value. As I am decreasing the value, I am getting low value. If both the flight speed are same, what will be my specific thrust? It will be 0. So difference is less, my specific thrust will also be less. If I am increasing the specific thrust, if I want to increase the specific thrust, that means I have to, the difference of the intake and the exit has to be more. Did you get the point? Please let me know.
The last point I want to explain once again.
This difference one.
Yes, ma'am.
Okay. Now very simple example. You can see here I have made some difference, right? Now what is that? F of, okay, let me clear everything, okay? Let me clear everything. Now f of s equals to, what is VE minus VA. Now I have considered first case is that 500 minus 100. What is 500? VE and VA is 100. Now what is the difference will I get? 400. Okay, this is one case. Case number 2, 500 minus 200, I will get 300. Okay. Now another case, let's consider 500 minus 100. We have 300. We will get 200. Right. Now what is this? Let's consider these are the difference. Okay, difference in the VE and VA. So what is happening? VE and VA, if I am increasing the difference, if I am increasing the del V, the difference of the velocity, if I am increasing, then automatically my Fs value will also increase. What is Fs? That is a specific thrust value will increase. I am talking only about the difference. However, either it is fixed or varying. I am only talking about the difference of the inlet and the exit. If the inlet and the exit velocity increases, the differences increases, then automatically my specific thrust will increase. For an example, if I keep 500 minus, let's consider 50, the difference is going to increase. So what I will get? 450, the difference is more. That means what is the value I am getting? I am getting more as compared with this one, right? So that is the fundamental understanding. That is another significance. Okay, that is another this is a change in velocity. Okay. All right. Yeah.
One second, ma'am. In the last point, there is one statement written that when Ci is equal to 0, it is of an important parameter. Like the thrust available, they are telling, ma'am. So what does that mean? Ci is equal to 0 means?
Ci means if VE is there, VE by VA equals to specific impulse. specific thrust. Okay.
Thrust.
Now, yeah, if Vs is that means Va is 0, right? Va is 0. The magnitude of specific thrust at V is 0 is significant. That means at this point, when we have the VE is a maximum point, that will be as a thrust available of takeoff. This is the condition they consider as a takeoff. What is a takeoff condition? Where when you have the flight, that means
There
initially
will be
when,
no inlet,
yeah,
inlet velocity. No?
there is no inlet velocity on that time, right? And that is the point we have the thrust available for the takeoff, right? You got the point?
Okay.
Huh.
It
And
means that it's being powered only by the GPU.
yes, absolutely. So more in
Okay,
detail you will
okay.
see the performance when you see the flight performance. So there you will have some graphical representation, the power, available power minimum, then during, during lot many conditions will be there, minimum drag. Okay. So again you will learn again these factors over there, both for the
Okay,
jet
ma'am.
and the propeller driven. Okay. Alright. Now again another significant terms, already we have gone through this one. This is for the turbojet. Okay, this is only for the turbojet. Now what it shows again, looking to this graph for the thrust alone. Look into the thrust. What it says, if it is a sea level, the thrust is 15,000 Newton, and if it is in the increase in altitude, we are increasing the altitude till 11 meter. What is the thrust? It is decreasing. So what it says that as we increase in altitude, the thrust decreases. As we increase in altitude, the thrust decreases. Then where the thrust is maximum? The thrust is maximum at the sea level. Thrust is maximum at the sea level. Okay. Next we have the SFC. Okay, how this SFC varies with an increase in flight speed. Okay, now again SFC play a very important role. Uh, so what you can signify from this graph? Can you tell me from the SFC what you can signify from this graph? What you understand from this graph?
At low altitude, it will be very high SFC.
Where will be very high SFC?
At low altitude means sea level.
At sea level, the SFC will be
Very
very high. Yeah, and as we increase in yes, as we increase in altitude, see this is for the 300
that
meter, the SFC will be slightly reduced. Okay, so as we increase in Mach number, right, as we increase in Mach number drastically varying with the altitude, it will increase only. Actually one step we can bring out two statements from here. Okay, one is at increase in Mach number, the SFC will increase. At increase in Mach number, okay, increase in Mach number, SFC will also increase. Now second statement we can give based on the altitude. As we increase in altitude, now altitude when we say, we can say the density decreases, right? When we say as we increase in altitude, what happens? The density decreases. So as we increase in altitude, we can find the SFC gets decreases. That means the efficiency will be slightly better. The efficiency will be slightly better. Clear? All right. Okay. Then, so what is, we can say the specific impulse is a reciprocal of the SFC. Can I say this statement? That means if I want to improve my specific impulse, that means my SFC has to be decreased. Okay. Now you can expect such kind of question from this particular graphical representation, that which among the proper jet engine will have the highest specific impulse. Okay, highest specific impulse. Now what kind of statement you can give from this particular graphical representation? What kind of statement? Which one is having the highest specific impulse? Now as I've said, specific impulse units are in terms
as
of
the Mach number is increasing, the specific impulses started to decrease, seen from the graph.
Okay, one statement we can give that if the Mach number increases, right, specific impulse get decreased.
It is decreasing.
Now I will go back to the previous slide. Okay, here. Now here when we discuss one statement, the specific impulse decreases at increase in flight speed, right? We have given the statement. Now can you see it has been proven over here also. As we increase in, either they say the speed in meter per second or kilometer per hour or in terms of Mach number. So basically this is a fact that as the Mach number increases, the specific impulse decreases. Now which one, now forgetting with the Mach number part, let's focus which among this engine will give the highest or the peakest of the specific impulse. Which one will be having the highest specific impulse?
Turbofan.
Yes. Now if you see that graph here, this is the range where we have the
maximum specific impulse.
Yes, maximum specific impulse. So you can see the turbofan will give the highest, then gradually we will have the turbofan with afterburner, then we have the ramjet, then we have the scramjet, and then we have the rocket. Can I say that if I have to write like specific impulse for turbofan will be higher than specific impulse of turbojet with afterburner will be than ramjet, specific impulse of ramjet, then specific impulse of scramjet. Okay, then we have the specific impulse of rocket, right? Can I say in this way? Right? Now this can also say in a reverse pattern. Now which one will be having SFC, high SFC? This is the specific impulse I am talking. If I have to talk about high SFC pattern,
It's a rocket.
Yes, absolutely. So the rocket will be having the high as compared with the turbofan, because they are reciprocal with each other. The specific impulse are reciprocal with the SFC. Alright, you got the concept? So always, yes please.
Hello, ma'am.
Yes.
We can also conclude that turbofan is higher efficient than these all these.
Higher efficiency. Now okay, here I cannot say the higher efficiency in this point, because these are the combination of air breathing and non air breathing engine. Okay, now if I consider, because their factor of VE and VI will vary, and where that efficiency is again a factor of this, right? So I cannot bring the efficiency point over here. Okay, so it is only about the consumption, the fuel consumption and the specific impulse, or I can say the thrust. right? So we cannot bring out the other factors over here.
While we are speaking
Efficiency
about the
factor.
efficiency point, while we are speaking about the efficiency factor, we have to consider the specific fuel consumption, ma'am.
Specific fuel consumption is there, but not in case of rocket. There are other factors also. In case of rocket, there are other factors that we cannot bring in the air breathing engine. Okay, that's why I cannot say that turbofan will be more efficient than the rocket. I cannot say that, right? Then why we have the rocket? We can use turbofan itself, right? So in that case, that's why I cannot state that this one is more efficient. Okay.
Then we shouldn't have included this rocket in this particular air breathing, ma'am.
Yes, of course, because since this graph is representing, so that's why I have included. Okay, because some of the question you can also get, like in one of the question paper they have asked, like uh, electrical propulsion. Okay, now they have given some couple of options and they have asked you to align that which among the uh, is having the highest specific impulse. Okay, so that's why I thought like I can include this graph, because once we go in the rocket propulsion, then you can quite connect the parameters well. Okay, so
Okay, ma'am.
all right, so
And one more question, ma'am. In
yes,
the
yes.
graph, I'm able to see some statement, ma'am. Theoretical maximum HC fuel. Like, what is that HC fuel?
Where is that? HC is a heat calorific values. Heat calorific value. Calorific value.
Ma'am, yes, ma'am. That I'm able to see the value as 42, but there it is given as H2 fuel. H2 fuel hydrogen. I'm able to see
Acha,
that.
acha, acha.
So
There, acha,
similarly,
acha.
similarly, HC means what, ma'am? I don't know.
HC is a, like hydrogen carbon fuel, like what we consider CH4, right? And
Okay.
like that. Okay.
Hydrocarbon.
Yes, hydrocarbon.
Okay, okay.
All right. All right. Then another. Okay. Before coming to this, we will come back to the slide. Okay. Now we will see another kind of efficiency. Now these formulas are very important in the problematic point of view and also from the significant point of view also. Okay, so they will give you some of the values and they will ask you to find out these other so and so parameters. Okay, so again comes the thermal efficiency of the turbojet engine. Now previously also we have seen some thermal efficiency which is as simple as this one. We have considered thermal efficiency is nothing but the ideal efficiency, Brayton cycle, which we have seen something like that, right? Which have seen. But in the question, if you see that thermal efficiency of the turbojet which you have given in terms of some velocity factors of the fuel ratios, then you have to use this formula. Okay, you have to use this formula. So what is this thermal efficiency means? It is a ratio between the propulsive power with an fuel flow rate into calorific value. Okay, so from that you can get this formula, something like VE square 1 minus of sigma. Sigma is the speed ratio into twice of F into CV. Okay, CV is a calorific value, F is a fuel air ratio, that is m dot F by m dot A. V is the exit or the jet velocity, you can consider 1 minus of sigma square. Okay, so if you have to use, they have to given the parameters, you have to use this formula. You have to use this formula. Okay. Now what the statement, we can bring down one more statement from here. So for an given certain amount of fuel and fuel ratio or the jet velocity. Now keeping the jet velocity, all those parameters fixed, if I'm keeping all the parameters fixed. Now how it is going to affect with the speed ratio? I can say that if I have to improve my specific if I have to increase my thermal efficiency, that means that Vi by Ve value has to be less, or I can say sigma value has to be less. If I want to improve my thermal efficiency, then that Vi by Ve or Va by Ve has to be low. Okay, has to be low. Now one more reason that why I am always writing the sigma equals to Va by Ve. Now that is also very confusing thing, that what is a speed ratio, whether it is uh, jet speed by flight speed or flight speed by jet speed. It is sometimes quite confusing. So always what I prefer is to remember any kind of formula with the help of the alphabetical order. So I know the sigma is a flight speed ratio. So I know Va, if I say Va means which is either can be ambient or the intake one. So A come first in the alphabetical order, so Va by Ve. Okay, this is another way you can remember in an alphabetical order. So what is meant by speed ratio? Okay. Now next we have, okay, next you can also combine this relation, the thermal efficiency, with an combustion efficiency. Okay, this is another formula. This is another very important formula. Many of the times they give these statements, and many times they have given the problem based on this particular formula itself. So you can rewrite this formula as eta Cc into Ve square minus 1 minus sigma square by 2 Cp 3 minus T02. This can also be rewrite in this form, eta Cc, okay, Ve square by 2 okay, in terms of this. Okay, you can also write as del H. Okay, del H. What is del H? Is a change in enthalpy. Change in enthalpy. Suppose in the question statement they will give you these are the factors, and they will ask what will be the change in enthalpy in the combustion chamber. So again, you know what is change in enthalpy is Cp into T03 by T02. Now this you have to use. Okay. Now this is another important statement. It says that for a constant value of with altitude and the turbine inlet temperature, that is a turbine inlet temperature or the exit of compressor combustion chamber is T03 value. Okay, if these values remain constant, what is a change in enthalpy? The enthalpy added by the combustion process is also constant. If this value is fixed and at constant altitude, right, the enthalpy added in the process in between this will also remains constant. This is another important statement. Okay, so simultaneously you can also bring out this conclusion. If the thermal efficiency reduces to 0, when it can reduce to 0? Once it will become, the alpha will becomes 1. What is alpha? That is a speed ratio becomes, that is Va by Ve, and or else you can also say that if the in flight speed becomes equals to the jet speed, if the flight speed is equal to the jet speed, what will be the affecting on the thermal efficiency? Then the thermal efficiency is going to be 0. The thermal efficiency is going to be 0. Okay, but again it says that logically it is not possible to be 0, but if such kind of question comes, then this is the another statement that you can bring to an fact. Okay. Okay. Now in case of turboprop, this is a formula. On that time you don't use any kind of propulsive power, okay, because thermal efficiency is a propulsive power by fuel into CV, right? So in case of turboprop you have to use a brake power. In case of turboprop you have to use a brake power equation. Now propeller efficiency, okay, propeller efficiency turboprop. Okay.
Can you just go back to the previous slide once, ma'am?
Yes, sure.
Yeah, 1 second. I'm just noting down.
Okay.
Yes, ma'am.
All right. Next we have propeller efficiency for an turboprop engine. Okay, it's a typo error, turboprop engine. So it is between the thrust power by the shaft power. So this kind of questions they can ask, like kind of small kind of MCQ, find out the suitable match the following, or they will give you the values thrust power and the shaft power. You have to find the propeller efficiency, and many of the questions they have asked such like that. Okay. So remember the formula is very important over here, the thrust power and the shaft power. Then propulsive efficiency, yes, it is another very important, you can say. Now propulsive efficiency we can denote by eta suffix p. It is the ratio between this propulsive power by the thrust power. Okay, sorry, it is the ratio between the thrust power by the propulsive power. It is the ratio between the thrust power by the propulsive power. Now both the thrust power and the propulsive power is already we have discussed. So when we substitute that value, you get something like this. You get some value something like that. So if I have to write, we can write in this way: 2 twice of VA by VE plus VA. Okay, if I have to write in terms of speed ratio is VA by VE. We can write like this: twice of sigma by 1 plus by 1 plus sigma. Okay. Have I done it correctly? Did I wrote it correctly? Just let me know. I think there is some error.
I think it is
1 by a
says there,
sigma.
ma'am, like,
1 by
it's
a
2
sigma.
by, yes, ma'am, 2 by 1 plus 1 by sigma.
Yeah, 2 by 1 plus of 1 by of sigma. So we can also rewrite this way, then twice of sigma, then sigma plus 1, right? We can also write this way.
Yes.
Right, we can also write this way. Okay, either 2 sigma by sigma plus 1 or 2 VA by VE plus VA, or we'll get like that.
Will you please show me the formula for propeller efficiency once more?
Yes, sure.
Okay, ma'am.
So what is the difference you can find here? Here we have the thrust power by shaft power, and here we have the thrust power by we have the propulsive power. Okay, that's a difference. Now to have the maximum thrust, okay, to have the maximum thrust, when we can have the maximum thrust, when the VA will be 0, and if the VA is 0, what we will get in this formula, if the VA is 0, the propulsive efficiency will also be 0, but again physically it is not possible, right? Now when we can get an maximum propulsive efficiency, when the sigma value will be, or inverse of sigma value will be 0. Inverse of sigma value will be 0, that is 1 by sigma will be 1. So inverse of that means either the VE by VA has to be 1, or sorry, same, has to be same, then only 1 by sigma or sigma by equals to 1, either of this statement. So then only we will get 0 thrust. Again the 0 thrust is not feasible. 0 thrust is not feasible. Now what point we can obtain the maximum thrust? At what point, the question comes is that at what point we can obtain the maximum thrust? So at what point we will get the maximum thrust? Can you let me know? What is the point that we will get the maximum thrust power? So if
The thrust power becomes the maximum when the CI is increasing.
CI is
The inlet, the or CA.
CA is increasing.
Yes,
See,
ma'am. The
there is
thrust
two
power.
conditions I have shown over here. Two conditions I have shown over here. Okay, one, if I want to keep my the flight velocity 0, right, my propulsive efficiency will be 0. Okay, propulsive efficiency will be 0. Now if I want to keep it maximum, I have to keep either to satisfy both my we have to keep it equal, the flight speed and the jet velocity has to be similar, same. Then what I will get? I will get the maximum propulsive efficiency, 100%. But what happens with the thrust? Thrust becomes 0. Okay, so this is the condition. Another condition is there for to obtain maximum thrust power. Okay, to obtain the maximum thrust power, we have to keep the sigma value, that is VA by VE is 1 by 2 or 0.5, and the condition is there to obtain a maximum thrust power, we have to keep the VA by VE has to be 0.5. Now tell me, what will be the efficiency of the, what will be the propulsive efficiency on that case? What will be the propulsive efficiency on that case?
0.66, ma'am.
That means 0.6, that means 66.67%. That means that is the, if you want to achieve the maximum thrust power of the particular engine, your approximately the propulsive efficiency should be approximately 66.67. That is another significant point. Another significant point. And next, the last one we will have is the overall efficiency. Okay, before overall efficiency, again we have, this is the formula for propeller driven engine. Okay, the propulsive efficiency That means for an propeller driven, okay, the propulsive efficiency is equals to the, can I say the propulsive efficiency is equals to the propeller efficiency, where we have seen the thrust power by the brake power. So in this, another significant point we can find from this graph is that as we increase in Mach number, we can see how this graphical parameter represents. Now for the propeller driven engine, you can see a certain amount of Mach number, the propeller efficiency increases. After, by increasing the Mach number, it gradually falls down. It gradually falls down. But in case of turbofan and turbojet, it is increasing with increase in Mach number. Now you can bring down many significant points from here, that for the propeller driven engine, the propulsive efficiency is fixed at some point, that is, it will be the maximum when it is ranging from Mach number 0.5 to 0.6. When the Mach number is ranging from 0.5 to 0.6, the propulsive efficiency will be the maximum. Once you increase the Mach number, the propulsive efficiency will fall. The propulsive efficiency will fall even though we increase in Mach number. Now second statement which I can give from here, that as we increase in Mach number without any limit over here, as we increase in Mach number, the propulsive efficiency for the turbofan will be more than the turbojet, more than the turbojet. Okay, can I say this statement? The propulsive efficiency both are increasing with increase in Mach number, but the turbofan, okay, turbofan propulsive efficiency will be more as compared with the turbojet. And the third statement, I can say that both for the turbofan and turbojet, the propulsive efficiency increases with increased Mach number. These are the important three statements that we can figure out from this graphical representation. Okay, both from this graphical representation. Then the last one, we will see the efficiency. The same goes over here. This from the here also you can bring down, if we have the bypass turbojet, or we have high bypass ratio or low bypass ratio, what is the impact? Again you can bring down the conclusion from here. The high bypass ratio, we will have more propulsive efficiency than low bypass ratio. Then we have the turbojet, right? Again you can bring down this conclusion. Okay, another one thing is the transmission efficiency. It is the efficiency ratio between the output of the transmission by the input of the transmission. So again you have to remember the formula over here. And moving to the last one, we have this and all we have discussed. Overall efficiency, yes, overall efficiency is a product of all the efficiency that we have seen, that is a thermal efficiency, transmission efficiency, and the propulsive efficiency.
May you show the transmission efficiency formula again?
It is an transmission is an output by input, output by input, power transmission.
I'm just looking at the formula.
Yeah. Output of the transmission by the input of to the transmission.
Okay, ma'am. Okay.
Alright. Now here we have to, when we talk about overall, you just have to couple up the things. Now in the question they can also ask you, like, find out the overall efficiency. They might give you the thermal power, they will give you the other stuffs what we require. But if they have not given the transitional efficiency, you just can consider this one as negotiable. Just neglect that. Neglect it. So if it is not there, then overall efficiency will be equal to the propulsive efficiency into the thermal efficiency. Okay, so these are the important formulas. Okay, so let me wind up the session over here.